Welcome, everyone. Today we are going to explore a beautiful idea in mathematics, one that has two completely different faces, but is, underneath it all, the exact same thing. The topic is, partitions are equivalent to equivalence relations, two sides of the same mathematical coin. My name is Prananath Patra, and I will be your guide through this journey. So let us get started. All right, let me begin by painting a picture for you. Imagine you have a group of 10 students, just 10 young people, standing together in a room. Now someone walks in and says, we need to organize these students. We need to group them somehow. Now here is the interesting thing. There are actually two completely different methods we could use to do this, and today we are going to learn both of them. The first method is called a partition. Think of it like this. You physically pick up students and put them into separate classrooms. Each student goes into one room. That is a partition. The second method is called an equivalence relation. Instead of putting students into rooms, you create a set of logical friendship rules. You decide who is connected to who is friends with whom. You are drawing invisible lines of connection between people. Now, here is the spoiler, and I want you to hold on to this thought for the entire video. By the time we finish today, we are going to prove, step by step, that these two methods, assigning students to classrooms using partitions and mapping out friendships using relations, are not just similar. They are the exact same mathematical idea. They are two different languages that say precisely the same thing. That is the beautiful surprise waiting for you at the end. But before we can group anything, we need to know what we are grouping. So let us meet our universe first. In mathematics, we call our collection of objects a set, and our particular set today we will call it S. S is simply a collection of 10 elements. Those elements are A, B, C, D, E, P, Q, R, S, and T. Picture these 10 letters just floating around, scattered in space. No organization whatsoever. No groups, no connections, no structure. Just 10 individual objects sitting loosely together. Think of it like 10 students who have just walked into an empty gymnasium. No assigned seats, no groups, nothing. They are just there. This is our starting point. This scattered, ungrouped collection is our set S, and everything we do today will be about organizing it. Now let us talk about the first method. What exactly is a partition? A partition is the act of drawing physical boxes around elements of a set. These boxes are called blocks, or sometimes classes. The idea is beautifully simple. You take your scattered elements, and you draw boundaries around them to group them together. But here is the crucial part. A partition is not just any random collection of boxes. It has to follow two very strict rules. If either rule is broken, it is not a valid partition. Full stop. Rule number 1 is called no overlapping. This means that each element of the set must belong to exactly one box. Just one, not two, not three, exactly one. The analogy here is perfect. You cannot sit in two classrooms at the same time. You are either in room A or room B. You cannot be in both. An element of a set works exactly the same way. It belongs to exactly one block. Rule number 2 is called no empty spaces. This means that every single element of the set must be inside some box. There is no element that floats freely outside all the boxes. The analogy here is equally vivid. No student can be left waiting in the hallway. Everyone gets assigned to a room. No exceptions. In mathematical terms, the blocks together must cover the entire set. Nothing is left out. So to summarize, a partition means drawing non-overlapping boxes that together contain every single element. No element is in two boxes. No element is in 0 boxes. Every element is in exactly one box. Now let us actually apply this to our set S and see what a partition looks like in practice. We are going to divide our 10 elements into 4 blocks. Think of them as 4 separate classrooms. The first block, which we will call P1, contains the elements A and B. Just those two. Imagine a blue classroom with just A and B sitting inside. The second block, which we will call P2, contains 3 elements, C, D, and E. A green classroom with 3 students. The third block, which we will call P3, contains just one element, page A, single student, sitting alone in their own classroom. And the fourth block, which we will call P4, contains the remaining 4 elements, Q, R, S, and T, a purple classroom with 4 students. Now let us check our 2 rules. Rule 1. Does any element appear in more than one block? No! Every element appears in exactly one block. Rule 2. Is any element left out? No! Every single element from our set S, all 10 of them, is accounted for in one of the 4 blocks. This grouping, this collection of 4 blocks P1, P2, P3, P4, is our partition. We write it as capital P equals the set containing P1, P2, P3, and P4. Beautiful. That is a partition. Clean, physical, and clear. Now let us completely change our perspective. Let us forget about boxes and rooms for a moment. We are going to think about the second method, equivalence relations. Instead of drawing physical boxes, we are now going to think about logical rules. Specifically, we are going to draw arrows between elements to indicate that they are, in some sense, equivalent to each other. For intuition, think of these arrows as friendship connections. Now, not just any set of arrows qualifies as an equivalence relation. Just like partitions had 2 strict rules, equivalence relations have 3 strict rules. And every single arrow in our diagram must obey all 3 of them. Rule number 1 is called the reflexive rule. This says that every element must be connected to itself. Every single one, no exceptions. In our friendship analogy, this means everyone is friends with themselves. In terms of arrows, we draw a little loop, called a self-loop, on every element. So A has a loop, B has a loop, every element has a loop. Rule number 2 is called the symmetric rule. This says that all friendships must be two-way streets. If element X is connected to element Y, then Y must also be connected to X. We draw double-headed arrows. If there is an arrow going from X to Y, there must also be an arrow going from Y back to X. No one-way friendships allowed. Rule number 3 is called the transitive rule. This is the most interesting one. It says that a friend of a friend must also be a direct friend. More precisely, if X is connected to Y, and Y is connected to Z, then we are required, not just allowed, but required, to also draw a direct connection between X and Z. We must complete the triangle. No gaps allowed. These 3 rules, reflexive, symmetric, transitive, are the defining properties of an equivalence relation. A relation on a set is an equivalence relation, if and only if it satisfies all 3. Now we arrive at the heart of today's lesson, the magical bridge connecting our 2 concepts. How do partitions and equivalence relations connect to each other? Let me give you a single rule, one simple, beautiful rule that creates a bridge between them. Here it is. Draw a friendship arrow between any 2 elements, if and only if they are sitting in the same box. That is it. That is the entire rule. If 2 elements share a block in our partition, we connect them with an arrow. If they are in different blocks, we draw no arrow between them. Now, the big question is this. Does this simple rule automatically satisfy all 3 of our equivalence relation requirements? Does it automatically give us reflexivity, symmetry, and transitivity? Let us go through our partition block by block, drawing arrows as we go, and watch the magic happen in real time. Let us start with our first block, the blue block, P1, which contains just 2 elements, A and B. We apply our rule, connect elements that are in the same box. First, A and B are in the same box together. So we draw a double-headed arrow between them, an arrow from A to B, and an arrow from B back to A. That gives us A connected to B and B connected to A. Notice, that automatically satisfies the symmetric rule. We got symmetry for free, just because we draw connections in both directions whenever 2 elements share a box. Second, A is in the same box as itself, so A gets a self-loop. B is in the same box as itself, so B also gets a self-loop. And that automatically satisfies the reflexive rule. We get reflexivity for free, simply because every element is trivially in the same box as itself. So from this small blue box with just 2 students inside, we have already demonstrated 2 of our 3 rules without any extra effort. The structure of the box does the work for us. Now let us move to the second block, the green block P2, which contains 3 elements, C, D, and E. Since C, D, and E all share the same box, we connect every pair of them to every other. C is in the same box as D, so we draw a double arrow between C and D. D is in the same box as E, so we draw a double arrow between D and E. C is in the same box as E, so we draw a double arrow between C and E. And of course, each of C, D, and E gets a self-loop. Now look carefully at what happened with the transitive rule. We have C connected to D, and D connected to E. The transitive rule says we must therefore also have C connected directly to E. And indeed we do, because C and E are both in the same green box. Transitivity is automatically satisfied, not because we thought carefully about it and made it work, but because being in the same physical box forced it to be true. The box structure guarantees transitivity. Think about why if X and Y are in the same box, and Y and Z are in the same box, then since blocks do not overlap, all 3 of them must be in the same single box. So X and Z must also be in that box. The connection is automatic, inevitable, unavoidable. We have two more blocks to handle. Let us look at the orange block and the purple block together. The orange block, P3, contains just a single element. Page poor P is all alone. When we apply our rule to P, we ask, who else is in the same box as P? Nobody. There is nobody else to connect to. So P only gets its self-loop. Just one element, one self-loop, and that is perfectly valid. A single element block is completely fine. It just means that P is not equivalent to anyone except itself. Now the purple block P4 contains 4 elements, Q, R, S, and T. This is the busiest block. Since all 4 elements share the same box, every pair among them gets a double-headed arrow. Q connects to R connects to S connects to T, Q connects to S, Q connects to T, R connects to T, and all of these go in both directions. Plus, each of them gets a self-loop. The result is a completely interconnected web. Every element in this block is directly connected to every other element. It is a fully connected cluster. Now step back and look at the complete picture. We started with a partition, 4 physical boxes with no structure, no arrows, just elements sitting in rooms. We applied one simple rule, connect elements that share a box. And what emerged, naturally and automatically, without any special effort, is a complete equivalence relation. Every element has a self-loop. Reflexivity is satisfied. Every connection is a double arrow. Symmetry is satisfied. Every chain of connections stays within a single cluster. Transitivity is satisfied. And notice something even more striking. Look at the final picture. No arrows cross the boundary between 2 different groups. Not a single one. A and B are connected to each other, but they are not connected to C, D, E, P, Q, R, S, or T. The clusters are completely isolated from one another. The boxes acted like invisible walls, and the arrows respect those walls perfectly. This is not a coincidence. This is the deep mathematical truth at the heart of today's lesson. The no-overlapping property of partitions is exactly what gives us transitivity. The total coverage property is exactly what gives us reflexivity. And the fact that we draw connections in both directions gives us symmetry. And now we reach our grand conclusion. A partition and an equivalence relation are not just related. They are 2 different ways of describing the same underlying mathematical structure. If you give me a partition, a set of non-overlapping, complete blocks, I can always construct a unique equivalence relation from it by connecting elements in the same block. And the reverse is also true. If you give me an equivalence relation, any relation satisfying reflexivity, symmetry, and transitivity, I can always recover a unique partition from it by grouping together all elements that are connected to each other. These groups are called equivalence classes, and they form a valid partition. So the 2 concepts are not just connected. They are 2 different lenses looking at the same object. The partition is the physical view, boxes, rooms, containers. The equivalence relation is the logical view, arrows, rules, connections. Choose whichever lens is more natural for the problem you are working on. They will always give you the same answer. And that is the beautiful mathematical symmetry we set out to discover today. Partitions and equivalence relations, 2 sides of the same coin. Thank you so much for watching. Take a moment to let this sink in, and I will see you in the next video. Please consider liking, sharing, and subscribing to join our gentle community, and I would truly love to hear your wonderful thoughts in the comments below.